probably not seen an inverse. You know what inverse operations are. What is the inverse operation of addition? What is the inverse operation of squaring? You're thinking about that. All right, so you have the idea of inverse operations. Inverse operations are the ones that undo one another, whereas inverse functions are a little bit different. Okay. Now, don't draw out these tables themselves, but I just wanted to show you to see if you can figure out what exactly happened to show the difference between a regular relation and then the inverse of it. If you look at those tables, what happens? And that's quite literally what inverse functions are going to be. Your x and y values flip. Let me show you a really, really, really easy example. When we're talking about inverse functions, first thing we got to remember is how do we know if something is in fact a function? How do you know if something is a function? Vertical line test, okay? It passes through that vertical line test. So if you have a graph, and just real idea, I'm just going to draw a linear graph. If I take a linear expression or linear equation, 2x minus 4, whatever, if this guy would in fact pass that vertical line. The vertical line would touch it at just one spot all the way through. Okay? If this graph happened to be an x squared, it would pass. If this graph was an x cubed, it would pass, and so on and so on. So we know that for the majority of the things that we've been working with, we've had functions all along. We know of one that was not a function. Sorry, that's more What's that? It's not a function. It's not a function. It's not a function because it was a parabola. It was a y squared parabola. Remember that? So it wouldn't pass that vertical line test. So that would not be a function. So this one would not have. We would say it's not a function, and so on. So what we do here is something very simple. If I take an equation y equals 2x minus 4. We all agree that's just a linear equation, and that would definitely be a function. You're okay with that? We know that for every value that you substitute in for value of x, you're going to get back exactly one value of y. For every part in the domain, there exists an equal one part of the range. So what we do to talk about the inverse of it is this. You flip-flop the x and y value, and you resolve for y. So if I flip-flop these two, and I resolve for y, how do I get y by itself? Add 4, right? So you get x minus 4 all over 2 plus 4. I was just making sure you're paying attention. Good job. You get x plus 4 all over 2, or if you wrote it out in terms like kind of the same way, it would be 1/2 x plus 2 is y. You okay with that? Now, in order to say that these two are in fact then what we call inverses, we do this whole, did you get it? You do this whole thing of, he's so proud of himself. Yeah. Now the other part was inside of it. The other part was inside. What happens in order to say that something isn't in fact an inverse? We have these two, right? Are you okay if I call this one f of x, and I call this one g of x? I know, I'm sorry. Watch what happens when you substitute it. What did that mean the other day when we wrote that out? Yeah, just substituting in. What that would mean is I would take the g of x equation, the 1/2 x plus 2, and I would surround it then with the f of x equation. Basically, it's saying that this g of x equation here is playing the role of the x value here. And then I do the same thing the other way around. So if I do that, I write down the 1/2 x plus 2. I surround it with the other one. What's 2 times 1/2? 1. What's 2 times 2? What's 4 minus 4? So what do I get? X. Okay. Do the same thing on the other one. When you do the same thing on the other one, start with the f of x equation, and then you surround it with a g. So if I do 2x minus 4, I take half of it, and I add 2. What's half of 2? What's half of 4? So I get x minus 2 plus 2, which is x. When you get inverse functions, when they substitute in for one another, they should always simplify to equal x. Always. Okay. Inverse functions, when you substitute in for one another, will always be equal to x to show that they are, in fact, inverses. This is a lot of that direct substitution stuff that we've been doing, but it's got a little bit of weirdness there thrown in. All right? Not too terrible so far. Right. All right. If I just want to find the inverse of this, we'll just do another quick solve. If I do another quick solve to find the inverse, that's y equals negative 2/3 x plus 6. I just want you guys to find the inverse of that real fast. Flip-flop x and y and resolve. Take a second and try that. Do you get the other one? Put it back together. Or better yet, take math notes and I'll put it together.
Yeah, laptop still needs into this 3D printer.
It's a 3D base. It's kind of cool. You just twist it to figure out where it goes. Yeah, just find the. It's super easy to start with. I'm not trying to get too crazy yet. So subtract 6. Sorry, I get distracted by this. It's shiny. So subtract 6. How do you undo multiplying by a fraction? Otherwise, we would say multiply by its reciprocal. And then distribute through, you get negative 3/2 x plus, what is that, 9? Okay. And that's just really quick, just finding inverses. Not dealing with slopes, just the reciprocal. I know, because it's linear and you're thinking, oh, should I do opposite reciprocals? No, it's just, you're just doing reciprocal. Yes, ma'am?
So then that would be the answer, or would you have to go back?
If it says just find the inverse, that's the answer. To verify it's an inverse, then you would go back and do that f of g of thing. Waiting. Yeah. Now, what happens here is that you're going to get to the point where things start to get a little bit weird. For example, not always are you dealing with linear stuff because, well, not everything is linear, obviously. It's crooked and turning stuff. So what happens is you have to start talking about the idea of when you have nth root stuff. And it basically works itself out to be be the same. Now, when we get to something like this, do you assume that anything is going to change when I have to verify inverses with nth root stuff? You don't have, nothing changes. You're still doing the same composite stuff we've been working on with combining like terms, using our exponent rules like we have been for the past few days. And that's why I thought that, getting into this and then what we're doing tomorrow all kind of melds to be the same. Yes, sir. You would have to, in order to verify, you have to do both f of g of x and g of f of x. Okay? That's how you verify that, in fact, they are inverses. So if I do that, first thing I would do is write down the g equation, x to the third over 2. And now that guy's playing the role of the value of x in the f equation. So I cube it, and I multiply it by 8. Okay. From here, I have my exponent rules. X to the third cubed becomes x to what power? 1. And what's 2 cubed? There's your x. All right. Go back to the other one. Do the same thing. Start with the f equation, 8x cubed. That's now playing the role of the value of x in the g equation. The 1/3 power means cube root. What's the cube root of 8? 2. And then 3 to the 1/3 is how much? 1. So I get 2x over 2, otherwise known as x. And it works. It's crazy how it works like that. It's the same basic principle, but you have some exponent rules to work with. All right? Yes, sir. Yeah. So you have to double check. Now, do you think that anything is going to change if I'm working with power rules? Oops. It gets a little bit weird when you find inverses of evens. Because why did they put that domain restriction on even? X can't be negative. Also, well, let me show you this. In order to find the inverse of x squared, I just rewrite it as y equals x squared. You okay with that? Flip-flop x and y. How do you undo squared? Square root it. So I get the square root of x is y. Now, normally I would say plus minus, but it says the values of x has to be greater than 0. It has to be only positive because can I take the square root of a negative? No. So now, open your calculators up real quick. I want to show you something that happens. When you have the equation of y equals x squared, if you have the equation y equals x squared and you look at it, it's just regular old boring parabola, but then it's only asking you to look at part of it, isn't it? You're only looking at everything from 0. So what I would do to adjust my window to see it better is I'm going to put my maximums, or excuse me, my minimums for both my x and my y value at 0. I know because it doesn't go below the y values here, so I'm just going to change my window. Y minimum, or excuse me, x minimum 0, and y minimum 0. And I get that. Next, I'm going to graph the square root of x. Same graph, leave it, and just put it on the next line down. Everybody see that? The red line is the square root of x, because that's the inverse of it. Now, what did these both equal if you substitute in for one another? Graph that line. Y equals x. They're symmetrical about that. The value, the inverses are always going to be symmetrical about the line y equals x, because they're inverses. Since if you substitute in for one another, you get x. So those two graphs, as one goes up, one goes away, each one of those points is going to be equidistant to the line y equals x. They're symmetrical about that. Remember how we talked about lines of symmetry, vertical lines of symmetry, or we had a horizontal line of symmetry with some of the ellipses, or even with the sideways parabola? You can get that to work. All right. Woo. Math is mathing right now. Pretty cool, huh? It just looks kind of cool. Yeah. We do that in pre-calc. All right. Now, the other thing I want to show you here real quick is, well, that's the reason why they have those domain restrictions, so that we can do the square root stuff. But the other thing that happens is that whether or not the function that you start with is going to, in fact, have an inverse. Think of it this way. If I go back to the idea of back this up. I go back to the idea of y equals x squared. What did that graph look like? It's just a parabola. I'm not putting a domain restriction on this. Okay? So it's just a parabola at y equals x squared. Now, if I inverse this without domain restriction, I get plus or minus square root of x, correct? Now, plus or minus the square root of x would look like, oh, that's a good one. It would look like this. Is that a function? No. So what happens here is that if your initial function, not just a parabola, but if your initial function won't pass a horizontal line test, its inverse won't be a function, because the inverse of that would not pass a vertical line test. Does that make sense? So if the initial function doesn't pass a horizontal test, its inverse won't be a function because it doesn't pass the vertical. That's the reason why they put on that problem a second ago, that domain restriction of just everything being positive, because if it was all positive, it passed that vertical test, which meant that its inverse passed everything vertically. Okay? So one of the ways that you can check to see initially if something will in fact have an inverse is to use your calculator and just look at a horizontal line test. Just see if it would work. For example, if I go back to the problem I had just up there, 1/2 x cubed minus 2. If I put in my calculator real fast, 1/2 of 0.5 x cubed minus 2, and I look at the graph. Back these out. Oh, you have to change. If you change your window, you have to change your window also. So I'm going to type 0.5 x cubed minus 2. It was minus 2, wasn't it? I'm just going to go back to my windows again. Just do a regular 10 by 10. That way you can see everything, at least start of it. 1/2 x, 0.5 x cubed minus 2. Does this pass a horizontal test? Yeah. Remember, this one's coming up and it's just changing direction at that when x is equal to 0. So this would in fact pass what we're calling a horizontal test for every it works going through, which means that will this inverse exist? Yeah, it'll exist because it'll be a function. So how do I find the inverse then of a cubed function? Well, what do you think I have to do? Switch x and y. Yes, ma'am. That means what would happen was, that's how it works. You would say find the inverse if the inverse is a function. And that's how you would quickly check to see if it would work. So like you were saying, Bradley, I would just flip-flop x and y real quick. So I'd say that x equals 1/2 y cubed minus 2. And then resolve for y. Add 2. Multiply everything by 2. And we're going to get, instead of, we're going to get 2x plus 4 is y cubed. And then how do I undo cubing? Cube root. And there's the inverse. There's the inverse of that function. So if you want to get real fancy schmancy, going back here, what was it? Math. Cube root, what did I say it was? 2x plus 4? It was plus 4, right? Okay. And they have to be symmetrical about the line. Y equals, not mode. Pretty cool, huh? I think it looks really cool when you start messing with these things. When you start doing a lot of inverse stuff, it gets really crazy. Okay? The problems I have for us tonight are pretty simple. They're really straightforward. We'll go through those. They're already uploaded, the PDF files there. We'll go through some of these tomorrow. I don't foresee this being horrible, scary, bad stuff, to be honest with you. It's just a matter of reading what if they're going to ask you whether or not something is a function before you have to do it, and then go from there. We'll go. The reason I also want to talk about these inverse things is because when we solve equations, you have to use inverse operations to get to them. Yeah. Let these guys put this up. You guys all got that? Which one, Ellen? This one?